we have observed that in case of the casting, we were discussing about the grain growth. You will have a main branch coming out from the solid liquid interface, and its propagation is in the liquid. So you see that there is a main branch or the trunk which is coming out from the solid liquid interface. And I have also told you that why they are formed. They are formed due to the instability of the solid liquid interface, because more and more of the solute is getting rejected into liquid melt, and the heat ahead of the solid liquid interface is conducted away. So that makes the solid liquid interface to become unstable, and then the planar solidification front. In case of the alloy composition, when solid particles are getting rejected, this solid planar solidification front is further breaks into the cellular type of solidification front or the dendritic type of microstructure. The scientists, in order to directly observe the solid liquid interface during the solidification, they have considered this transparent organic material that solidifies like metals with the help of one material, which is your carbon tetrabromide. So this is a special type of organic material which has a resemblance of the solidification as that of the metals. Based upon the solidification of this particular material, as this is a transparent material, and the mold in which they have solidified this particular material, this is also transparent in nature. The transparency in that mold cavity and the transparency in this carbon, this tetrabromide material, has enabled them to capture the solidification microstructure using the in situ metallography. So with the help of high speed recording system, or with the help of combining it with the high resolution microscope or electron microscope, they have observed the solidification mechanism in this particular material. First type of solidification is a planar solidification, in which this solid liquid interface is vertical and it is plane. B is a type of cellular solidification with a small amount of impurity. If you add some impurity in this particular material, carbon tetrabromide, and then you vary the temperature gradient or the cooling rate you will have this type of solidification, which is cellular solidification. And then this choice is a kind of dendritic microstructure where you have an arm, and from the surface of this main arm, more of the branching is occurring. So this is the solidification, which is your columnar. This is also in column form, but you can observe that this is having some dendrites or branching structure. This fourth one is your Equiaxed dendritic microstructure. So you can observe that the dendritic arms are very big and the spacing between them is also large. In this Equiaxed dendritic solidification, you see the grain boundaries. Within the grain boundary, you can observe the small size dendritic arm, and this dendritic arm makes a particular crystal, which is, you can say, the size of these crystals or the grains are equiaxed of equal size. So this is equiaxed dendritic solidification, and that happens due to the rapid solidification. Similar types of solidification are observed in metals or in your welded components of alloy material. Now you can understand that you have different types of solidification or the microstructure which can occur in the welded structure at different regions. I told you in our previous slide, there is a temperature gradient which is varying from region to region. So you will have a different type of microstructure. You may have different type of microstructure in the same molten pool. And now you can learn that how we can observe such type of solidification in our welded component. Scientists have observed that under the condition of low solidification rate, the low solidification rate was denoted by this R value, and steeper temperature gradient. So the temperature gradient is very high and solidification rate is slow. So both plane front, and if you are having these both condition, then you have the planar front solidification that is occurring in the molten weld pool. You can see this is the fusion boundary. Here is your base metal, and ahead there is your weld metal. In a very small region, you can observe planar solidification occurring in the material. In this case, you can observe the fusion zone, the base metal, and the grains of the base metal, which have this preferentially growth direction. I told you that the new grains formed at the surface of the grains of the base metal, they will grow in this particular direction, which is your 110, which is a preferential direction of the easy growth. And this type of solid liquid interface is planar in nature. Okay. But however, in most practical cases, This condition is very difficult to achieve when you have the low solidification rate and high temperature gradient. If there is a high temperature gradient, the solidification will also be very fast because the heat will remove at a faster rate. In most of the practical cases, the planar front breaks into other modes described either by the cellular mode or more complex dendritic morphology. You can see this is the case when actual welding is going on. This is a case of autogeneous welding of Fe49 nickel. So this is a kind of particular alloy which they have considered and they have performed the autogeneous welding. Autogeneous welding, I told you that in autogeneous welding there is no requirement of the filler metal as there are thin sheets to be joined. So in such case they have observed that initially they were having this planar solidification. So this is a particular region where you have observed the planar solidification, but further it breaks down because there is a change in the temperature gradient and also there is a change in the solidification rate. So that results in the cellular type of solidification region. Okay, there is a shift of planar to cellular transition in the autogeneous welding of 49 nickel material, alloy material. Okay, and similarly you can say this is cellular growth. If you look from this side, you will observe this type of cross section in which you can observe that there is a hexagonal shape of grain. This is a main grain, and within the main grain you have small cells formed which are the subgrain. This particular type of condition is known as coring. Coring in solidification, and this type of microstructure is not desirable. I told you in most practical cases either the cellular microstructure is observed or the columnar dendritic microstructure is also observed. This is the base metal and from the surface a new grain is developing or which is having a central arm and then a small branch sub-branching which has occurred, and this is also occurring in the form of long columns. However, the main or the internal microstructure is dendritic in nature. And the fourth one is the Equiaxed microstructure, in which you can observe this type of microstructure where you have the Equiaxed type of dendrites. So this is the sub branching, and all this particular dendrite all are of them almost of the same size. As I told you, the solidification mode, composition, solidification, temperature, and solidification rate determine the solidification mode in welded components. In most casting, you will observe either this cellular growth or the columnar dendritic growth. Initially, I told you that your planar solidification front, which is unstable, this is the unstable region due to the rejection of the solid atoms or solid particles into the liquid melt and the rapid conduction of the heat from the solid liquid interface. So that interface become unstable and then it breaks into the cellular front, and for a short period or short distance again it changes into the more dendritic morphology depending upon the solidification conditions. In this diagram you can observe that this is the base metal, and from the base metal initially the planar front was advancing into the liquid melt, and then from the planar melt this solid liquid interface becomes unstable, and from there the cellular type of grain growth is occurring, and further it breaks down in the form of the dendritic microstructure within the fusion zone. This diagram shows the transition from planar to cellular and then from cellular to dendritic microstructure. In case of 110 aluminium welded components, and they were using this 4047 type of material. So 110 is also an aluminium alloy and 4047 is also an aluminium alloy. So I told you that in case of the welding, what is your main aim? Your main aim is to improve the microstructure or the mechanical property of the welded section. So you can achieve that if you take the filler wire of higher composition or the better composition, that will result in the favorable microstructure. Sometimes you can also add the alloying elements with the help of filler material so that it improves the microstructure and the properties of the welded section. In most of the alloys, the solidification is occurring initially up to some distance. It is the planar in nature, and then in most of the cases it breaks into cellular and a combination of these. I told you the solidification mode is determined by the degree of constitutional supercooling or undercooling. So undercooling, what is undercooling? So cooling below the freezing point is your undercooling, and constitutional supercooling is a condition when the solid is rejecting into the liquid and the heat ahead of this solid liquid interface is also conducting away. The liquid ahead of the solid liquid interface will experience a kind of automatic cooling known as the constitutional supercooling. So this constitutional supercooling is occurring due to the change in the constitution, in the change in the solid composition. Okay, this is the solidification mode, and as the extent of supercooling increases, more of the solutes is rejected into the liquid melt, more dendritic mode or the dendritic arm will form into the, and it will favor the dendritic mode of the solidification. In case of this fusion welding, the common solidification modes are either the cellular or cellular dendritic mode. So this type of cellular or cellular dendritic mode are commonly observed in case of the welding and the casted components. And Equiaxed dendritic growth is also not normally observed in fusion weld due to the large constitutional supercooling required. Means extremely large constitutional supercooling means very rapidly rejection of all the solute particle into the liquid melt and in a very short interval of time. That is also very difficult practically in most of the conditions of the industrial application. This is very difficult to achieve, but the scientists under sophisticated instrumentation and with the help of controlled heat input and favorable, you can say, easy to control microstructure or the elemental composition, in all such laboratory conditions they have also observed this type of cellular dendritic growth, which we have observed in case of carbon tetrabromide. This we have already observed that cellular, you can say this is the cellular. So the one was the planar, other was the cellular, and then the cellular, you can see the cellular arms were converting into somewhat cellular dendritic, means some small dendrites are also formed on the surface. This is the cellular dendritic growth, and further and finally at the end they are more converted into the dendritic form. From this diagram you can observe that how you can achieve the different type of solidification modes. So on the y-axis they have represented the temperature gradient, which is denoted by GL, and on the x-axis they have represented the solidification rate. Suppose if you have managed to work in this region, you will observe Equiaxed type of dendritic structure. For that, this temperature planar type of microstructure, what you required a higher temperature gradient and a low solidification rate. If you increase or decrease the temperature gradient and solidification rate, you can get this type of microstructure. They have plotted two regimes. One is of very high GR value and other is of low GR value. So this type of regimes also depends upon the type of the welding process and the composition of the weld metal or the base metal used in this particular welding process. Suppose you are working in the regime above the higher GR value, so you will observe this finer microstructure, and in this case you observe the similar type of microstructure but of the finer scale. But here in this region or below this region you will have this same type of microstructure, but the size of the grains will be large. From this mapping you can easily predict that where you are going to fall, which type of microstructure will be formed in your welded zone. So if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.